Hi everyone, today we'll be presenting our results from Experiment 8, the synthesis of alum. This experiment demonstrates how a common industrial compound can be synthesized in the lab and verified through various analytical techniques.
Alum might seem like a simple compound, but it's actually quite interesting. When we say alum, we're typically referring to potassium aluminum sulfate dodecahydrate, which is quite a mouthful. It's part of a larger family of double sulfate salts, and there are several different types. The ones we crystallized in lab contains potassium, aluminum, sulfate groups, and water molecules in its crystal structure. Speaking of those water molecules, this brings us to an important concept: hydrates. The 12H2O in our alum's formula tells us that for every unit of salt, there are 12 water molecules incorporated into the crystal structure. These water molecules are essential to the crystal's structure and properties. What makes alum particularly interesting is its variety of practical applications. You might be surprised to learn that you've probably encountered alum in your daily life. It's commonly used in water treatment plants as a purifying agent, in the food industry as a pickling agent, and even in cosmetics as a natural deodorant. Let's focus specifically on its role in water treatment, as this is one of the most important applications. When alum is added to water, it undergoes a chemical reaction forming aluminum hydroxide. This forms a gelatinous precipitate that acts like a net, capturing suspended particles as it settles. This process, known as coagulation flocculation, is crucial for providing clean drinking water to millions of people worldwide.
We had a few goals for this experiment, which we broke up into 4 categories. First, chemical synthesis. Our primary objective was to synthesize potassium alum, specifically potassium aluminum sulfate dodecahydrate. This involved transforming aluminum, a simple metal, into a more complex ionic compound. We also aimed to use a purification technique, recrystallization, to ensure product quality. As for yield analysis, we had 3 specific targets. We wanted to calculate the theoretical yields based on our starting materials, measure the actual product yield we obtained in the lab, and lastly, determine the percent yield efficiency of our synthesis. These measurements will help us evaluate the success of our procedure. For product verification, we implemented several qualitative tests to confirm we had synthesized the correct compound, which we'll talk about later in our presentation. Lastly, this experiment allowed us to develop important technical skills. We used vacuum filtration techniques, practiced recrystallization procedures, and lastly learned proper temperature control methods, which are all essential skills in chemical synthesis. Moving on to the materials and methods of this experiment, I want to start off with the overall balanced equation for the synthesis of alum, which is pictured on the top right of this slide. This equation can be read as 2 moles of solid aluminum plus 2 moles of aqueous potassium hydroxide plus 4 moles of aqueous sulfuric acid plus 22 moles of liquid water yields 2 moles of solid potassium aluminum sulfate dodecahydrate, which is our alum, plus 1 mole of hydrogen gas. Now I'll explain how we executed this reaction in the lab. We started with about 0.5 grams of aluminum metal, which we cut into small pieces, and added a 4 molar potassium hydroxide solution. In this step, we observed a fizzing exothermic reaction, indicating the formation of our intermediate product. For our filtration steps, we utilized a Buchner funnel setup. We did this because a Buchner funnel setup is crucial to obtain a clear solution. As you can see in the picture on the right, the filter flask is connected to a vacuum, which helps sufficiently separate our product from any unreacted materials. We did this twice to achieve the clarity we needed. The third step was the careful addition of acid. We added a 9 molar sulfuric acid and then concentrated our solution to about 50 milliliters using a hot plate, and then we placed this solution in an ice bath for about 20 minutes to promote crystallization. Finally, for purification, we performed a second vacuum filtration to collect our crystals. The recrystallization step was vital for improving the purity of our final product.
This slide focuses on the qualitative tests used to confirm the success of our synthesis. Each test was designed to verify a specific property of the alum product. We're going to go over these and tests. We're going to go over these tests and the results. First, the hydrate test was performed to check for water of hydration in the alum crystals. When the product was heated, water droplets formed, indicating the presence of hydrated water molecules and key characteristics of potassium aluminum sulfate. Next, the flame test was used to identify potassium ions. When the sample was introduced to a flame, it produced a distinct violet color, which is a characteristic indicator of potassium. The solubility tests were used to verify the presence of sulfate and aluminum ions. When barium chloride was added to the solution of the product, a white precipitate formed, confirming the presence of the sulfate ions. Also, the aluminum ion test involved adding excess potassium hydroxide to the product solution, which dissolved the aluminum containing precipitate, further confirming its identity. Finally, a pH test of the alum solution revealed an acidic environment which was consistent with the chemical properties of potassium alum sulfate. And together, these qualitative tests demonstrated that the synthesis was successful as expected and all properties of the alum were confirmed. In this slide, we're going to be talking about the key findings and conclusions from our synthesis experiment. The successful formation of alum was evidenced by the production of white crystalline product, which is expected appearance of potassium alum sulfate. Um, the overall yield of the synthesis was measured at 42%. While this percentage reflects that some of our material was lost during purification and filtration, it's still a reasonable outcome given the complexity of the process and the steps that we had to take as well. The qualitative tests further confirmed the identity and purity of our product. An example being that the hydrate test we performed showed the presence of water molecules in the crystal lactase, defining which is a characteristic of alum. The flame test that we also performed verified the presence of potassium ions, as evidenced by the violet color that we got. Similarly, the solubility test demonstrated the presence of sulfate and aluminum ions consistent with the product's expected chemical composition. And finally, our pH test confirmed the solution's acidic nature, which aligns with the properties of alum.